researcher at the University of St Andrews. I'm here to answer your questions about condensed matter physics and physics in general. Over the last week, we've received loads of amazing questions, and I don't have time to answer them all. But here are my answers to my top 3 questions. Margaret asks, how do humans get electric shocks? One way that humans can get an electric shock is if they connect themselves to a live power supply. So say I put 2 screwdrivers into a plug socket, then I would get a nasty shock. Obviously that is a terrible idea, you should not do it. What happens then is that I've just made myself part of an electrical circuit, and actually in terms of main supply, one with a very high voltage, which means quite a lot of current could flow through me and I would get a bad shock. But a less serious way that you might get a shock is from static electricity. And you might have felt this before, say when you've taken a jumper off. You might hear a bit of crackling, or maybe your hair starts to stick up. What happens there is that when you've taken your jumper off, is you've rubbed 2 insulating materials together, and you've actually transferred electrons from one material to the other and left an imbalance of charge. Now, if that's on an insulating material, like your jumper or your skin, it's got nowhere to go. But if you were to then go and touch something metallic that conducts electricity, that excess charge is free to flow from you onto the conductor, and you might feel that as a nasty shock. So less serious than plugging yourself into the mains, but still unpleasant. Probably best to avoid both. Cameron asks, what is absolute zero, and has it been observed or just theorised? Absolute zero is a theoretical minimum temperature. We might think that 0 degrees C is quite cold, but actually that's nothing, because absolute zero is at minus 273.15 degrees Celsius, or 0 Kelvin. Let's think about what temperature actually is. Temperature is a way that we label the energy of a system, and that can relate to some other property, say the particle motion. So let's think about some gas particles at room temperature. They're actually jiggling about a lot. They've got a lot of thermal energy, so they can move quite freely. But as we start to cool them down, they move less and less and less. And there's some minimum motion that these particles can have. So we can't actually make them move less than that. So likewise, we can't take them to a lower temperature than the temperature that minimum motion is at. So that's where our limit comes from. But we can think of this in terms of thermodynamic variables, say pressure. Pressure and temperature are related, and we can measure that relationship. As we decrease the pressure, something's temperature also decreases. So we could use that relationship between pressure and temperature to define a temperature scale. And it would make sense to start that scale at absolute zero, which is actually what that Kelvin temperature scale is, or where that 0 Kelvin comes from. It starts from absolute zero, and it uses a thermodynamic relationship to define temperature. We can't actually get there though, because to cool something down, we have to take energy out, and we call that doing work. But to make something exactly zero would take an infinite amount of work, because we'd have to keep chipping away, but we'd never actually be able to get to zero. And that's before we even think of the experimental considerations, like keeping it perfectly isolated and not letting any heat get in. We can get close though. In my lab, we use a special kind of fridge that mixes together 2 types of liquid helium to cool things down. And that gets us to 0.05 Kelvin. But to the real low temperature physicists, that's nothing, because they can cool things down to about a billionth of a degree, And they can do that either by trapping atoms with lasers or by using magnetic fields to cool nuclear spins. So we might never get to absolute zero, but we have got quite close. James asks, what makes squishy things squishy and hard things hard? That is basically condensed matter in a nutshell. These hard materials might be metals, semiconductors, crystals. There's one thing that they have in common, and that is a very regular arrangement of the atoms that make up the material. And we call this regular pattern a lattice. And actually, it can be different bonds that hold the atoms together. That depends on where that atom is, or that mixture of atoms are in the periodic table. And that regular arrangement and those relatively strong bonds give that material some rigidity. Soft matter, on the other hand, is quite different. That's where we have this sort of squishiness. And what that squishiness really means is that we can deform or move those molecules quite a long way from their equilibrium or their starting position with a really small amount of energy. That's something we can't do with the hard materials because they're held in that tight lattice. It's very difficult to move them at all. So what's going on here? Well, actually, if we were to look on that small, that almost atomic scale, things would look very messy and disordered. It's only when we look on the larger scale that there's any sort of structure at all. So if we take the example of jelly, what we've got here is a big tangle, like a bowl of spaghetti of these protein molecules. And there's water molecules mixed in there as well. But what the protein molecules actually do is that they form crosslinks between the molecules, and they almost form like a large net that holds the water molecules in place. Now that means that we can actually deform or push those molecules quite a long way, but it will still hold its shape or structure to some extent, because there's still some links between the molecules, but it's only quite a loose structure. And that's really what makes the jelly wobbly. And that's where most forms of squishiness can come from. It's that these materials only have quite a loose structure. They look a lot more disordered than those hard structures, the regular lattice. And actually that's what makes soft matter so interesting. So definitely go find out more if you're interested. I hope you all enjoyed these answers. Next week we'll be answering questions about magma, minerals and geology. If you haven't done already, send in your questions to this email address here or post them in the comments below by Friday the 24th of April. Thanks again for watching.